This is Dr. Brothers, and I'm going to be doing the lecture part selection for ECE 3872, Design Fundamentals. So the first thing we're going to talk about, whenever you're going to try to find parts, you have to look at the datasheet. The datasheet gives you all the information. This is also called the technical specification or the specification document. It contains performance, technical characteristics, voltage levels, current levels, connection types, package footprints. So, for example, you might want to look up a datasheet. You might find a datasheet for a DC motor, and it'll give you the operating temperature, the rated voltage, the rated load, the non-load current, the no-load speed. All the information that you could want is going to be found in the spec sheet. Oftentimes, these spec sheets or data sheets are extremely detailed, several pages long, that contain every piece of information you could ever want. Other times, they're one page and they barely contain anything. It's frustrating to try to figure out what it actually is. But no matter what, this is the place you start. So when you're looking for parts, when you're looking for a beginning point, a good place to start, if you're just looking for generic ideas, SparkFun, Adafruit, Polio, blah, I can't even say it, P-O-L-O-L-U. These are more of hobbyists. They contain some really interesting circuits, some ideas, some makerspace type stuff. If you want to go to a more industry-focused place, you can go to digikey, Newark, Mauser, and then if you're looking for raw materials, McMaster, Home Depot, Granger, all of these sites have a wealth of information, and pretty much any type of mechanical on the raw materials, those are a lot of the mechanical stuff, the electronics, digikey, Newark, you're going to be able to find almost anything you could ever imagine if you can search through it. So here are some rules of thumb. Examine the datasheet first. Only select an active part. In stock, check the shipping options. So example, if it's not inside the US, it's going to take more time. And then buy multiples if possible, because there will be a break as you go up in quantity. The biggest thing, if you're doing a prototype, contact the company. Oftentimes they'll give you free samples, because think about this from the company's point of view. If you say, hey, I'm an electrical engineer, I'm working on a prototype, I'm wondering if I could get 5 of these parts in order to sample and see if they'd work for our application. Most companies will be more than happy to send you some parts and let you try them out in hopes that you're going to actually produce. A lot of these even have, like, it's such a common thing that a lot of the manufacturers' websites that you go to will have a link for free samples. And in there, they'll ask, if it goes to production, how many will you be ordering? 100, 1,000, 10,000. So this is a really, really common practice, and it's a good thing to know about. Inside the ECE department at Georgia Tech, we have some great resources. Or the first people that you should go and talk to, James Steinberg and Kevin Ferry. Their contact information is shown on this slide. And then the Interdisciplinary Design Commons, the IDC. Here's their website. This is also known as the Hive. This is the makerspace located at Van Leer. They can help explain a lot of what you need and help you fabricate a lot of the parts that you might need to do your capstone design. So at the end of this presentation, I'll show a couple of Excel sheets from James and Kevin about the commonly stocked parts in the ECE department. So let's go through a couple of the different sections. So first, we're going to start off with mechanical design. So materials. You want to think about things such as density, strength, flexibility, durability, cost, thermal expansion, conductivity. All of these different the different characteristics that you might not think about when you're first looking at doing something as a design. Wood, rapid prototyping. This is great. It's really cheap. They have a laser cutter in the IDC where they can laser cut out wood and put an edge on it that'll allow it to lock together with another piece of wood. Really easy way to make boxes, to make a lot of things. Acrylic, easy to cut. Again, the laser cutter, not strong. But the acrylic and some of the polycarbonate, it's great to get different colors into it. Some of those are also clear. PVC, easy to work with. UV will break it down over time, so you need to paint it. But a lot of things, if you're trying to make something like an electrical conduit or something like the arms of a robot, going to Home Depot and getting a length of PVC, really cost-effective means of creating mechanical linkages. Aluminum doesn't rust. However, it'll fail under repeated loading. So think about bending a paper clip. You bend a paper clip back and forth, eventually it's going to break. That's aluminum. Copper. If copper is going to be flexed repeatedly, so think if you are moving it through a mechanical connection in a robotic arm, you want to think of stranded wire versus solid wire. The solid wire, that hard core, is going to be harder to bend. The stranded wire will allow for more flex as it goes. Steel, I mean, it's great, but it rusts, so you have to paint it. It's also a little harder to work with. In the makerspace, they have metalworking tools, they have welders. You can make pretty much whatever you want, all the way from laser cutting some very lightweight wood to building something in steel. Composite, reinforced carbon fiber, costly, brittle, high strength to weight ratio though. So a lot of things, if you want to make something that may be more UAV centric, something that's going to fly, composites might be the right way to go. Tolerances. This one will get a lot of people. If you have pieces that fit together and you want to make something that's going to slide like an actuator that's going to push a rod, you have to think about how tightly those pieces are going to fit together, and you have to think about situations like thermal expansion. Is it going to lock down, especially if you're using different types of materials? It might bind. So really consider this and really consider how you're going to do your moving parts, pieces that fit together and pieces that slide. So usually what you do when you're specifying something, you specify where it's going to be and then you specify a tolerance. So you have to consider the two tolerances put together of, for instance, the pin that you're going to make and the hole that it's going to go into. How much expansion does that need? And if the tolerance is, if the pin is made big and the hole is made small, it might not fit. So these are considerations that you have to have when you're working with mechanical applications. Definitely try to make sure that you're not going to make mechanical parts that bind. And if possible, when you're putting things together, use a commercial fastener, such as a hinge or a ball joint, so that you don't have to make precision parts. One other thing on this topic, a lot of people don't consider it, but it's very hard to cut a square hole. So as you're doing your designs, and you might say, oh, okay, I'm going to make a square peg, and it's going to go into this square hole, and when the two lock together, that will give it the ability to turn. Well, creating an actual square is very hard because we're using bits to bore down and cut that square opening. Unless you're 3D printing it, and even then the head of the 3D printer is going to move in a little bit of a smooth motion. So consider that. Try to think about ways that you can simplify the mechanical aspects of your design. All right, on to mechanical parts. Motors and actuators. These are the basis for getting any motion in our machines. And for the most part, everything that you're going to find in a motor, you can get an equivalent in an actuator. Actuator moves linearly. So it's going to push the end out or pull the end in. oftentimes what it is a motor that's driving a linear gear. So we have DC motors. Small DC voltages gives a constant rotational speed. Cheap can be voltage plus or voltage minus connectors, so you can switch the polarity. And if you switch the polarity, it'll reverse the motor. You have servos. Servos are DC motors, but they also have an angle sensor and encoder, a feedback controller, and they're used to control over a position of the motor shaft is important. So meaning they have very fine control of where the motor turns relative to where it's at. So very high precision motion. It's only going to work on a positive voltage. You cannot apply a negative and reverse the direction. So it works off voltage positive and ground, and then it has angle/control connections for the feedback and the sense of where the servo is at currently. You have a DC motor combined with a gearbox. These are used to convert rotational speed to torque. So it usually slows it down to produce a higher output torque. The gearbox oftentimes will be incorporated to the end of the motor so it looks like a single package. We have stepper motors. These are motors that move a precise rotational, meaning they click. They go tick, 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 tick. So every pulse sent to it, it will move one tick. Angle control is done by counting pulses. They are expensive and they are heavy, but they're very, very well-defined motion control. Linear motor. This is when it's translated into, it is translational instead of rotational. So that's what I'm talking about the actuators where it's moving straight in and out. Solenoid is a linear motor constructed, operated typically with two positions. So meaning, if you have a solenoid, you have an open and you have a closed. So one of the common applications for a solenoid is to hook it up to a water valve. So you can either open the water valve or close the water valve. But yeah, you can apply a voltage to it and it will pop the solenoid, remove the voltage, and it'll shut it back down. So oftentimes these are spring-loaded, two positions. All right, for DC motors, there are a couple of different types. Brushed motors. These are two wires, power and ground, continuous rotation motors with average reliability. These run at high RPMs, mostly controlled by a pulse width modulation for variable speeds. What the pulse width modulation does is it gives it a different integral of voltage. So if you only apply a small duration of time, that's going to charge a capacitor just a little bit because it's going through kind of a low-pass filter when it goes into the motor. And so it will be seen as a small voltage over time, and so it'll go slower. If you send in a pulse for the entire period, it's going to fully charge that capacitor and it's going to run at full speed. So the less time you give it voltage, the lower it'll go. Usually these will also run if you want to send in an analog voltage. The same result will happen. So advantage, these are low cost, high torque, quick starting and stopping. Disadvantages, they have physical brushes that touch the rotor and they go out. So high EMI, they get noisy because after a while those brushes, as they're touching, they start to spark and they give off EMI. So speed control is not good. Poor regulation, not good. So these are cheap motors that will run. So these are a really good option if you just need something that'll run. A lot of the lower end, like power drills, run with brushes. And after they run for a while, you have to pull the brushes out and replace them. So here are some examples. This is the next type. This is a brushless motor. So these are higher cost, and control can be complex and expensive. So what they do is these actually convert into an AC motor, a three-phase AC motor, in order to spin the internal. So you have the permanent magnet on the inside, the exterior, you make an AC rotating magnetic field by alternating the DC. So it's actually converted over into an AC current to move this around. Servos, They have built-in control circuitry with feedback, as I mentioned earlier. They use a PWM for control. Unlike regular DC motors, servos cannot be hooked up backwards. Don't switch the polarity or you'll burn them out. These are very efficient power-wise. These run 80 to 90% efficiency. They do not suffer from vibration issues. They have good speed control throughout the entire speed range. They don't generate much heat because they're so efficient. They have high position control on their accuracy. However, it consumes power with or without a load, and it can be expensive because you're always running that control circuitry. That's why it consumes power all the time. Here's some examples of some servos. You can see this bottom one has a gearbox on it, and it's a DC motor, and then it also has the control circuit at the very bottom with a potentiometer to measure how fast it's going or how far, but really high degree of precision on the motion. Stepper motors, this is one step further than the servos. And this can be seen in the illustration where it has these small steps that can move. So every time a voltage is applied, it will move forward by one step. And so these have oftentimes they'll have high torque and real great control, but they're expensive. Okay, going with motors. This is kind of, if you want to think about it, the inverse of a motor. A motor, you apply a current to it, and the result is a motion. In this one, you're going to apply a current, and through the interaction of the magnetic fields, it's going to generate, through the Hall effect, it's going to generate a magnitude of the electronic field, and it can measure current. These usually have a through-hole type design where you'll run the wire through the center of it. Sometimes they have clamps. Here are some 3-pin Hall sensors where you can switch these up. So if you want to sense current, there's ICs that you can buy, and you just put them into your design. ADCs and DACs, these are wonderful, but there are also so many of them that you can't even count. So analog to digital converters and digital to analog converters, they convert between the analog to digital or digital to analog domains. They have a lot of characteristics, specifically the number of bits, the digital interface, the sampling rate, the spectral content, how noisy they are. The larger the bandwidth, the noisier it's going to be because it has more energy in that noise floor. Microprocessors. A lot of times people will think that, oh, I'm going to just get this MCU that I've used in this other class and apply it. So don't just use the same one you've always used. We have PICs, Peripheral Interface Controller, very low cost, usually only a couple of dollars. These are 8-bit processors, very low power. These guys are great. They're cheap, they're efficient, you can do a lot with them. Now we go up, there's a microcontroller unit. Usually they're 10, 20, they might be up to $100, but they're usually not that expensive. They could have one or more cores, CPU cores, built-in memory, programmable input-output peripherals. These can get fancy. They can have a bunch of different built-in hardware cores to go with them. Then we can go up to the next stage, such as the ARM core processors, Arduinos, Raspberry Pis. Usually these can run Linux. They're based on an instruction set architecture. They can cost anywhere from tens of dollars to thousands of dollars. So you have the whole gambit of possibilities. All right, I'm going to jump over real quick and bring up digikey. Let me stop just 1 second and share the screen. So here is digikey, and this is a really, really great wealth of information about everything electrical. And so we're going to go through a real quick example of what to do here. So consider that I'm looking for a 4148 diode. Say that we breadboarded a circuit, and when we did the breadboard, we used one with leads to push it into the breadboard. Well, now we want to do our PCB, and so we want to go and look for the same component but we want to switch from the wired to a surface mount. So what I did, I searched for the number, the 4148 diode, and it comes up and it says here are a bunch of different arenas where we can see these diodes: LEDs, diodes, logic buffers, TV diodes, but I'm going to go to the top one, diodes, rectifiers, single. And if we just scroll through, you can filter by a whole bunch of stuff. We can see the first comes up with an image of a diode with the wires. This is probably what we used when we breadboarded it. What we want is a surface mount. Let's see, where's the surface mount one at? Was that a surface mount, or did it just not have leads on it? There we go. There's the diodes incorporated. So we might want to, this is the one I'm looking for. Here we go. That's all we want. A nice simple diode. So you can see surface mount. Now, the first thing I said, we need to look at the data sheets. So, well, we want to look at first the cost. And is it an active part? And it usually will tell you where it's shipping from. We might have to go in to see where it's at. Oh, and here's the filter where we can filter through surface mount and the voltages. But let's go and look at the data sheet. So we can go in and look at the data sheet. So here's an example of a data sheet and what we can find. You can see where it has the illustration of which end is the anode and cathode, and the one, and so this end is the cathode, this end is the anode. And you can see all the electrical specifications. And here are some standard usage circuits, or let's see, is this a recovery time equivalency test circuit? So you can put in this test circuit, run it, and here are the graphs that you should get, so the characteristics of the device. And then we're going to go into a whole bunch of temperature curves, and then the mechanical packaging, and the soldering footprint. So if this part does not exist in your PCB tool, you can go in and make a soldering footprint from these dimensions so that you can make the landing pads appropriately. So this is an example of a common circuit data sheet, and everything here is on digikey. Very easy to search for. And we can see if we go to this data sheet, similar, very, very, very similar information. There are all the graphs and performance for it, and then the statistics of how big it is and all the information. So those are those parts. Let me bring up one more item real quick. There are a couple of different stock sheets that we have available through the different through the ECE shop. There it comes. Give me just a second. And so you can see here is a part sheet, and this is posted to Canvas. So please go to Canvas and look at this. Here are a lot of the transistors, the BJTs and the JFETs, BJT, another BJT, a digikey link, part numbers, in stock, fuses. One of the things that is a requirement on our capstone design is that everything needs to be fused. Here's Moser, here's digikey, diodes. We have Zener diodes. We have, let's see, does this have any of the ones that we were just looking for? The 4148, there's a 4148 right there. Converters, DC to DC converters, op amps, capacitors, digital ICs, AND gates, OR gates, JK, flip-flop, counters, XOR. Let's see. Miscellaneous components, other ICs. So contact James and Kevin to find out more information about those. And then there is another list. If you look at this list, here are sensors, distance sensor, accelerometer, and the list goes on and on. Look at all these pages of sensors. Wireless communication modules, wired breakouts, power and voltage converters, motors and actuators. Here we go. Look at all these that are in stock. Now, one of the big things about our project, we are talking about a cost limitation in our capstone design. You need to really consider that as you're picking your parts. Microcontrollers and processors, these are the ones that they keep in stock or that they can easily order for you. And so you can see that a lot of these are in stock. And so we have Arduinos, we have Raspberry Pis, BeagleBoards, PICs. Look at all these. So go ahead, look through all the equipment that is currently in the lab and try to make sure as you're doing your part selection, you're going to use something that they are currently stocking instead of getting some exotic type of part that might take a while to actually get in. So again, if you have any questions about this lecture, please feel free to give me an email, give me a call, hit me up during office hours, whatever you need. We have a lot of resources for parts. Spend some time going through them, looking at the data sheets. Really try to get to know these parts a little bit before you get too far down the road in saying, we're going to use this one because we use this one in another class. Open up your possibilities. We have a lot of options. Take some time to look them over. All right. Have a good one.